Hello everyone. In this session, we are briefly going to discuss about what categorical cross entropy loss is and how is it different from the binary cross entropy loss or log loss that we already have dealt in case of binary class classification problem. So in case of binary class classification problem, you always had one neuron in your output layer, and whatever raw logit values that you had, you basically have passed it through a sigmoid function which generated the values in between 0 to 1. We call these values as probability values. The probability of yi being equal to 1. So the target variable in case of binary classification problem was either 0 or 1. Okay, so this is what we have perceived, and whatever loss function that we have considered was the binary cross entropy loss. We also call this binary cross entropy loss as log loss. First, let us try and understand what categorical cross entropy loss is and how is it different from binary cross entropy loss. Categorical cross entropy loss comes into picture in case of multi-class classification problem. In case of binary classification problem, you had this sigmoid function plus binary cross entropy loss. This is for binary classification. Multi-class classification problem, you will have softmax activation function which considers different logit values as input and then generates the relative probabilities that we already have discussed. It is used in conjunction with the categorical cross entropy loss. To generalize the equation for or the function for the categorical cross entropy loss, it's generally given as minus summation of I equal to 1 to c yi log pi. If you observe this particular formula, it is in some way related to the entropy that we have learned during our decision tree module. For those who have taken my course, you clearly have understood how you derive this particular formula and what entropy is all about. But there are subtle differences. It's not exactly the same. However, categorical cross entropy loss here measures the difference between two probability distributions, one of which is going to be the actual or true distribution which is given by P. The other one here is going to be predicted probability distribution or predicted distribution, which is Q. So yi here is expressed as the true class labels. So yi here is going to be the true or actual labels here. Pi is going to be the probability values associated with different labels. Let us consider a scenario where your target variable is having only 0 or 1. Now let's expand this particular formula. C here is number of classes, right? So now I'll have summation of I equal to 1 to 2, whatever it is. Now whatever formula that we are having now gets reduced to minus yi is going to be 0 multiplied by log pi plus 1 multiplied by, or probably I can rewrite this as yi itself. Yi log pi plus 1 minus yi here. 1 minus yi multiplied by log 1 minus pi. So this is a log loss formula that we already have looked at. So this equation or this formula that we are currently observing is log loss function, which is nothing but the binary cross entropy function. So categorical cross entropy is a more generic notation. This can also be treated as a binary cross entropy loss whenever your target variable has only two classes associated with it. In case of multiple classes, you can expand it to the number of classes. Like you'll have as many number of terms in this particular equation as the number of classes are. Okay. So whenever you are having n instances, so this was only for one instance, only for one observation within your data. If you are having n instances, obviously you need to iterate this process or you need to compute your loss for all of these observations, where the number of observations here are I is equal to 1 to capital N. So there are n different observations. So now you are taking an average. So here it should be 1 by n. So minus 1 by n, summation of I equal to 1 to n, summation of j equal to 1 to c yi log pj. Right? So sorry about the typo. We need to have this 1 by n here in the formula because we are just trying to take the average loss that's computed across the different instances or different observations that you had. All what we are trying to assess here is to identify how far away is your predicted distribution from your actual or true distribution. That's what error is all about, right? So now let's look at practically implementing this using Python. Also consider a particular example and then try and understand the nuances behind it. Okay. So let's get back to this particular coding exercise where I'm essentially going to define a particular tensor object called as z. So torch.tensor, and I'm going to provide some raw logit values here. The logit values here could be 2.0, minus 1.0, and zero point 0.1. Right? So these are my raw logit values. I'm also going to define what my actual y values are. So this is for one instance. So this is for one instance or one observation that we are considering. Okay. So obviously, let's say that the label associated was 0 here. Considering the target has got labels of 0, 1, and 2. Target labels are 0, 1, and 2. So this particular instance has got this particular label as 0. So now I can express this as a tensor object and do one hot encoding for this. I'm doing one hot encoding for this as 1, 0, 0. Since the label is 0, this first value within this particular list here is going to be 1. The remaining are going to be 0, indicating that the observation has got this target value as 1. Sorry, this target value as 0. Target value as label 0 here. And I'm converting all of them to floating point. So d type, I'm setting it as torch dot float 64. Okay. So anyways, these are represented as floating point numbers itself. I need not explicitly convert them to float as above. Okay. So once we have all of these required tensor objects created, let me go about defining the loss function, which is my cross entropy loss function. So I'm calling it as loss now. Invoke this function called loss by making use of both the logit values that we are currently having as well as the actual y values that you're having. So whatever loss it is, so it gets computed. So there's some error, it states that expected input batch size of 1 to match the target batch size of 3. So obviously this has to be provided as list within list, which was a typo. Now you get the loss. The loss value is going to be 0.1818. So now let's go about considering the formula that we already have dealt with. So what was the formula? So minus summation of I equal to 1 to C, and then yi log 1 or log pi. That's all, right? So now let me expand this particular formula for whatever values that you're observing. All right. Minus 1 multiplied by whatever 1 that you are having here. This should get multiplied with the corresponding probability value. But these are logit values. I have not converted them to probability values yet. So torch.sigmoid, sorry, torch.softmax, and provide this z within the parentheses is going to generate me the corresponding probabilities. This has to be across the dimension 0, sorry, dimension 1. So this gets us the values. This gets us the probability values here. So whatever probabilities values that you are observing here are associated with these different raw logit values that you have in the previous statement. Now 1 multiplied by the corresponding probability value, which is going to be 0.8338. The remaining are nothing but zeros. So I'm not actually expanding this equation further. And obviously I need to provide log here. So np.log of 0.8338 is now going to generate the loss value as 0.1817, which is exactly matching with the loss that we have computed using the built-in function called cross entropy loss. So here, whatever mathematical formulation that we have learned a while ago, we have implemented it for the given tensor object. Tensor object comprising of different logit values for one instance here. We can also expand this to having multiple instances. Let's say that there are 3 instances or 3 observations within your data. And the labels are going to be, very first observation had got label 0. The second observation has got label 0 again. The third observation had got label 2, so 002. Okay, these are the actual values, which I have typically represented them as one hot encoded values. So likewise, we'll have logit values corresponding to all these 3 different observations here. Let's say that this is 2.9. This here is going to be 0.3. I'm just giving some random data, where I'm trying to keep it in line, where I'm trying to keep these raw logit values in line with whatever predictions that whatever actual y values that you're observing. Since the actual y value for the last observation is label 2, I'm going to give an arbitrarily higher value for this when compared to the other 2. All of these are good predictions. All of these are good predictions. If your predictions are bad, let's say that I'm having a arbitrarily higher value for one of these logit values. So typically you should observe a higher logit value for this particular element. But now I have amended this particular tensor object in a way that I am observing a higher logit value for the second element. The loss is going to increase from 0.18 to a higher value. It's going to be 9.00. Since this is a bad prediction, right? I believe you have understood what I'm trying to explain here. Anyways, now let me get back to this particular code. So now you have defined 3 different instances or observations with all of these actual y values and all of these different logit values corresponding to each of these observations. Now let's compute the loss. The loss is very minimal since all of these are good predictions. Let's say that this is 200. Now this is going to be a bad prediction. As per this particular logit values, now the predicted label is going to be label 0 and not label 2, since the logit value corresponding to label 0 is going to be very high here. So the overall loss, which is now 0.09, is going to increase like anything. It's going to be 126 because of that. So let me revert back the code. So the overall loss that we are observing is minimal now. All of these predictions are good predictions that we are observing. So you can make use of the same softmax function that we already have dealt with and then rerun this particular code. So now you are observing these different probabilities that are associated with different observations that we have defined in the previous step. Likewise, you also can consider max function and provide whatever loss that you are observing, whatever z values that you are observing across this particular dimension 1. This is going to generate these values, right? But now if you're clearly observing, so this here is predicted label for the first instance or first observation, which is label 0. And that's what we are observing here. The label 0 again for the second instance, the predicted label is also reporting the same thing. And it's going to be label 2 for the third instance, which is same as what we are currently observing in your y actual values. The corresponding logit values, the corresponding maximal logit values 2, 2.9 and 10 are now being reported here. Okay. If I'm going to change this particular data from 2 to 200, and then obviously the last prediction is going to be a wrong prediction. The loss also is going to increase now. The last prediction here is going to be label 0 itself, since we are observing a higher logit value for label 0. So all the predicted labels are now 0, 0, 0. And you are also observing the corresponding logit values that you have typically observed to be the maximal of the given logit values for every observation. I believe we are pretty much clear on trying and understanding on how you compute the categorical cross entropy loss in case of multi-class classification problem. Whenever your target is having more than 2 different class labels associated, how are you going to compute the loss that you are currently observing? How are you going to generate these probability values, these relative probability values associated with every single instance that you have produced? Also look at the predicted labels for each one of these observations that you have provided as input. Okay. So this reduces to binary cross entropy, especially when your target has got only 2 labels associated with it. We typically also have looked at the formulation by expanding the generic notation that we had. We also have understood the formulation that we have arrived at was same as that of the log loss that we already have learned. Okay. So I now clearly am assuming that you are well aware of the difference between binary cross entropy or log loss and categorical cross entropy loss and when to use what. Okay. That's pretty much all I wanted to discuss with you in this session. And thanks for watching.